23 of teaching physics. So in this time, I'll be teaching you about types of waves versus wave motion. So first, I'm going to teach you what a wave is. A wave essentially transfers energy through harmonic motion. If you don't know what that means, harmonic motion is basically like these wavy thingies. Okay. All right. So there are two types of waves. One wave is a mechanical wave, and one wave is an electromagnetic wave. So a mechanical wave, so the big difference between them actually is that a mechanical wave needs a medium to move through. So that means it needs to like travel through something. So like air or like water or something like that. It can't travel through a vacuum where there's nothing. But an electromagnetic wave does not need a medium to travel through. So that's why light can travel through space and sound can't travel through space, because space, there's no medium in space. So mechanical waves can't travel through. Any questions so far?
No, not really.
All right. So now we are going to move on to wave motions. So wave motions are not wave types. Just to make that clear, because a lot of times they are confused with each other. Wave motion is how the wave moves. So there are two ways that a wave can move. One of them is called transverse motion. So that is this first one here. So a transverse motion is the matter, as indicated by these lines. They oscillate in a up and down direction. So they move up and down like this. And the energy that it's pushing is moving that way. So the oscillation of the material is perpendicular to the direction of the energy transfer. So you see these like high points and like low points?
Yeah.
So this is called these are called crests and troughs. Trough. I think that's how you spell trough. I'm not sure. These are the highest points and the lowest points of a wave. And this middle point here is called the normal. Okay. From the normal to a crest, or from a normal to a trough, that is called the amplitude of the wave. So like how high it goes or how low it goes relative to the middle. And from here, from crest to crest, or from trough to trough, this is called the wavelength. Okay, so that is transverse motion. And next one is longitudinal, which is down here. So longitudinal waves, how it works is it's the material and the energy transfer are parallel. So the material pushes this way, and the energy that is transferring is also going this way. So that is the main difference between the two types. And see these areas of big space? that is called a rarefaction. And this small space here, where all the lines are tight together, that is called a compression. So remember mechanical waves, right? So mechanical waves can have both transverse motion and longitudinal motion, but a electromagnetic wave can only travel transversely, so it can only travel like this. Any questions?
Yeah. So would the wavelength of the longitudinal wave be the like distance from one rarefaction to the other?
Yes. Good observation. Any other questions?
I've heard a lot about like frequency in waves. So like, what would the frequency of like, say the first wave be?
Okay, yeah. So frequency in waves is sort of like speed. So like you can think of it as speed, sort of. So frequency is basically how fast it can go. The wave moves from up here to down here. So like how fast it can do this. Right. And then, yeah, so that's a frequency. So, yeah, and then for the longitudinal, I'm pretty sure it's basically the same thing. It's just how fast the matter pushes the energy, I think.
Wait, wouldn't it be 1 over the wavelength or something like that?
I'm not sure. I don't know the math yet. I think our next takeaways thing is math, but I'm not sure yet. Anything else?
No.
All right.
Just search it up.
All right. That is the end of our recording. Okay, welcome to part 416 of teaching physics. So this time I'll be teaching you about wave equations and variables. So remember the vocabulary I mentioned yesterday?
Yeah, like the amplitude and like the
wavelength.
Yeah, and like the troughs and like the crest.
Yeah. All right, so I'm gonna basically put those into like sort of math terms. Okay, so first is a wavelength. So like I said, a wavelength is just the length of one crest to one crest or one trough to one trough. And so that is measured in just any distance units, so like meters and stuff. And the symbol for it is lambda, that thing. The next is frequency. And a frequency is how many waves pass through a certain point per unit time. So how much stuff passes through, let's say, this point per second. That's a frequency.
Yeah, so it's kind of like speed of the wave, I guess.
Sort of. Speed of like, yeah, sort of. And that's measured, that symbol is F. And the last is period. And period is sort of like the inverse of frequency. Instead of how many waves pass through a certain point per unit time, is how much time it takes for a certain amount of stuff to pass through this point. So it's instead of being measured in like oscillations per second, it's measured in seconds per oscillation. So okay, and the symbol is italicized T. So we can say T equals 1 over f. And then same thing for here, we can say f equals 1 over t. Any questions so far?
No, not really.
Okay. So another equation we have is for the speed of the entire, or velocity rather, of the entire wave. So that equation is v, standing for velocity, equals the wavelength multiplied by the frequency. And in a electromagnetic wave, this v is equal to the speed of light, because electromagnetic waves is just light. So when this is talking about an electromagnetic wave, this is the fastest anything known to man can go. So the speed of light. And that's basically it. Do you have any questions?
No, not really.
Not really. All right. Well, I guess that's all we have for today. All right. Part 6 of physics. So today I'll be teaching about wave speeds through different mediums. So I'll talk about sound waves, and then electromagnetic waves. So a sound wave travels longitudinally, and it has to the sound has to bump into molecules in the air, right? Because it's a mechanical wave and it needs to travel through a medium. So the more stuff in the air there is, the faster the sound will travel. So sound will travel fastest through a solid because the molecules are very close together. So as the sound hits each molecule, they'll keep bouncing, and it'll go relatively quickly. In a liquid, it will be a little slower because the molecules are farther apart. But the slowest is gas, because gas molecules are the farthest apart. So when the sound hits them, it takes a while for them to bounce against each other. Any questions so far?
So what happens when sound moves through a vacuum?
Yeah, so since in a vacuum there's no matter, right? Or in a perfect world, in a perfect vacuum, there's no matter, so sound can't actually travel through a vacuum. So I'll go on to electromagnetic waves. So electromagnetic waves, they don't need a medium to travel through. So that means it travels really fast through a vacuum since there's nothing in its way. So that's why the speed of light, so light traveling through space is the fastest thing known to man, because there's nothing in its way and light is really quick. And then when it gets to gas, the light slows down a little bit because there are some molecules in the way. But one thing to keep in mind is that as it travels through these different mediums, the speed of the light doesn't change. The speed of the light is still a constant c, but since there's molecules in the way, it has to maneuver around them, which technically slows them down a little bit. So in a gas, it slows down a little bit, and then in a liquid, it slows down even more. And then a solid, well, you can't really shine light through a solid. At least not visible light. So, yeah. Any questions?
So why is it that light can go through a vacuum but sound can't?
Yeah, so like so a light is a is it wait, what's that wave called again? So remember when we talked about wave types and wave motions?
Yeah.
Yeah, so hold on. I'm just gonna pull on it. What the? So there are two types of waves. One wave can travel without a medium. And one wave cannot travel without a medium. So like sound waves is a mechanical wave, so it can't travel through a medium. So that means there needs to be matter for it to travel through, right? So like there's no matter in a vacuum, so a sound can't travel through a vacuum.
Oh.
Light, it doesn't need a medium to travel through because it like oscillates off it kind of builds on itself, so you don't really need anything for it to travel through. So yeah, that's why.
Oh. Okay.
Is that all?
Yeah.
All right. That's cute. Okay, this is the last teaching. Yay. No. Okay. So today I'll be teaching you about the Doppler effect. So, okay. Have you ever like stood by the side of the road, and then a car came by and it was like honking its horn, and then like you hear the sound changes as it passes you? Has that ever happened?
Yes.
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 All right. So and that's what the Doppler effect is. So the Doppler effect affects the frequency of a wave. It can be light or sound. So here's what happens. Normally, no wait. Normally, this is. Oh no. Wait a second. This is what happens when something sends out like a sound or light. Like it's sent out uniformly. So like these are uniform circles. Distance. Let's just assume the distance between these are the same. So when you hear it, the sound is the same. But when something gets close to the speed of the wave, okay, so this is a wave, right? This thing's a wave. When something gets close to that speed, let's say a car, this is what happens. The car pushes the waves so that the frequency here is a lot smaller than the frequency that you see back here. So as the car comes towards you, the sound you hear gets a little higher pitched. But right as it passes you, so let's say you're a man, you're standing here, and then the car passes you, it's going towards you from this side, you hear this. So it's really high pitched. But as it passes you, you'll hear this. It's really low pitched. So that's the Doppler effect. Any questions so far?
So like when the car passes you, you like receive like the waves that are really far apart. So like that makes it lower, or does it make it like higher, I guess?
Yeah. Okay. So like it's got a lower frequency, so it makes it sound lower.
And does it make it like softer or something?
Oh no. The volume has nothing to do with this. This is just frequency of the wave.
Okay.
The volume would be like amplitude, like how up and down the wave goes.
So amplitude would like change over time here.
No, it wouldn't.
Okay.
And then also this also happens to light. If you go close enough to the speed of light, which is not possible, if you looked at like a red sign, when you pass by it, well, like something red is like going at the speed of light. When it comes towards you, you'll see it as red because that's wait no, you'll see it as blue because it's the same principle. Like it's it's compressing the frequency, so like the frequency gets a lot higher, so it'll look blue. But as it passes you, the frequency will look a lot longer, so it look red as it passes you.
So you're saying that like red light has a lower frequency than blue light?
Yes.
Okay.
Any other questions?
No. No.
Alright, that is conclusion of our Zoom session.